Okay, so we need to deal with satellites moving in a circular fashion now as well. First off, what do we mean by a satellite? Well, the obvious one is it's a satellite relaying information from one point in the Earth to another point in the Earth, but it could also be a moon traveling around a planet. So our moon traveling around the Earth, or another moon traveling around a different planet. A satellite around the Sun then could be any one of the planets themselves. So it's any orbiting body that travels around a larger mass, essentially. Okay, and the idea here is that if the satellite is going in a circular fashion, it must be experiencing a centripetal force to cause it to change direction constantly. And in this case, the centripetal force is the gravitational force. Now watch what that does. If we left the gravitational force equal to the centripetal force, so gmm over r squared equals mv squared over r. One of the m's will cancel, that's the mass of the satellite itself. One of the r's will cancel, and then we get v squared is equal to gm over r, so v is equal to the square root of gm over r. Now g is the gravitational constant, m is the mass of the body at the centre of the circular path. So in the instance here where we have an actual satellite going around the Earth, m is the mass of the Earth. If the moon was going around the Earth, m would be the mass of the Earth. And then if we had something like Jupiter and one of its moons, we'd say Titan, then the mass in that formula would be the mass of Jupiter. Or if we had the Sun and, let's say, Mercury going around the Sun, then the velocity of Mercury can be calculated from g by the mass of the Sun over r. And r is how far the satellite is away from the centre of the planet it's orbiting. What's important about this is the velocity of the object, which is a tangent to that circular motion at all times, is not dependent on the mass of the object itself. It's only dependent on the mass of the planet around which it's orbiting and the radius or the distance that it is from the centre of that planet. Now, there's another way of looking at it, and that is replacing the radius of the circular motion with the radius of the planet and the height above the surface. So if you look at the diagram at around 8 o'clock there's a red line set, with r next to it, that's the radius of the circular motion. If I broke that radius up into the radius of the Earth and added on the height above the Earth's surface, we'd get the following formula. And sometimes you'd use one, sometimes you'd use the other, but in reality they're the exact same thing. So in the new image, we still have the g, which is the gravitational constant. We still have the mass of the planet around which the satellite is orbiting. The r there, the capital R, is the radius of the planet, and the h is the height above the planet's surface at which the satellite is orbiting. That big R plus h equals the little r to the right of it, which is just the radius of the circular motion. So it's the same thing. Okay, so what about the period of the circular motion? Well, if we decided that we wanted to use speed as distance over time, so that's kind of the second paragraph there, velocity is displacement over time. And then if we said, we know the formula for the velocity, which is root gm over r, if I wrote the distance travelled by the satellite as the circumference of a circle, the distance travelled would be 2 by pi by the radius of the circular motion. So then what we get is v is equal to 2 pi r over t. However, if we square both sides, and then we know v squared is equal to gm over r, we get gm over r is equal to 4 pi squared r squared over t squared. And then when you cross multiply, you get this formula t squared equals 4 pi squared r cubed over gm. That thing is called Kepler's law, or more correctly Kepler's third law, and it shows there's a relationship between the period and the radius of the circular path for a satellite. And the relationship is t squared is proportional to r cubed.